Now start to look at the electrical power in single-phase AC circuits. Let's start at the active power. And you know that it's a product of the voltage and the current. As you can see up here, we have the part of the voltage and the current as we had previously with these magnitudes. With some trigonometric relationship, you can see here, we can now come up to this equation, this expression here. And what is interesting here is that you can actually see that we have one constant value and one sine curve with double frequency. When talking about power consumption in an electrical circuit, it is the mean value of the instant power over a period of time. So then you take the integral of the period, and by doing that with some calculations, we can come to a very simple expression looking like that. So here you can see the plotted curve over our resistance, and you can see for both voltage, current and the power. Here you can see the voltage curve, and then you have the current curve here. And of course then the power is the sum of multiplication of voltage and current. And you can see it's positive, and it's also then oscillating around the mean value, as we already calculated the dotted line, as you can see here. So this is pure resistance power oscillating. When it comes to the reactive power, pure now with inductance, you will actually see that we have an oscillating curve around the abscissa, with the same area above and below. So this means that the power inductance consumes power for part of the period, and it emits again for the next part of the period. And the net power consumes no power in the inductance actually. So this means that this effect oscillates. It's a pulsating power, back and forth in the circuit, thus increasing the current in the wires and thus increasing the active power in them, since the wires contain resistance. So this is a very basic but very important fundamental understanding. We can also use the same approach for the active power equation. Now we put into a pure 90 degrees between voltage and current, and we can get this expression here. So it will have a double frequency at the voltage and current, and this will be having a look in the oscilloscope, where you have the voltage and the current, and then you have the reactive power oscillating. This is where the pure reactive power then, of course. Another very important aspect on the electric power is of course the power triangle, as you can see here, inductive, and the power triangle, as you know, it is an active power and it's a reactive power part, and it's apparent power. So we can use basic trigonometric relationships. So we have, you know, that the apparent power can be calculated from this with square root of p squared plus q squared. And actually we can insert the expression for them, and we can get this one for the apparent power. We also can use expression like this, where we have the current square and the impedance and the cosine to the theta. So this is equation. As we know, and you can see here, we have then the reactive power, and in the grid we typically have, it's very connected to the voltage, and it's often provided locally, and it actually helps P to flow. And the primary source here is the synchronous generator. At the same time we have the active power, where it's very strongly connected to the frequency and is independent of location. And actually, as I said, need help from the reactive power Q to flow. And also, of course, the primary source is the synchronous generator, especially here in Norway. And typically we can have a glass of beer like this, and it can represent the transmission line. And where the foam is the reactive power part, and the active power is actually liquid. So that's actually producing something. So, but the total amount will be filled up with both the Q and the P. So the transmission line will be full in the same manner. So due to its presence, the system cannot be utilized up to its limits, we can express. Another very important part of the power is the power factor. And the power factor, you can see up here, is the cosine to the angle in the power triangle. And it's the active power divided on the apparent power. So this means like how much of the active power is the apparent power. To the left here you can see the power diagram, and at the same time you have also the impedance diagram. And this expression, we can see that the angle of the power diagram for this one-phase circuit is the same as the impedance angle. We can also usefully have a reactive power factor. It's the sine to the angle, where you have the reactive power Q divided on S. Another also part of the power factor, we can express it in this fashion or in this fashion. And you will probably need that in your exercises. As you can see here, we have the QL, the inductive part is in arrow this way, and you have the reactive part, QC, in the opposite. So actually they work against each other. And so then we have the possibility to have an improvement of the overall power factor. So typically we can have a lagging power factor in what you see here. We have inductive load. For example, you have a power factor of 0.8 lagging. Then you can put a capacitor in parallel, and you can have a 0.95 lagging. So that means that this vector will come closer to this vector, and we have a reduction of this angle here. So typical lower current is drawn to the load, and that will of course reduce the line loss of the system. Now we will look at the complex power, which we will mostly use from now. And a way to understand that is to look at it mathematically. So here we have two vectors. We have a current vector and we have a voltage vector. So a vector is of course a length and an angle. So the phi here is the angle to the current, and the phi is the angle to the voltage. And the angle between them is the phi. So the complex power can be defined as the voltage times the current in complex conjugate. That means that we're changing the angle of this current. So if you see, if we did not do that, if you do not change the angle, the sign of the angle, we will have a phi u plus phi I, and the vector will actually be different. It will be not the correct power, because we need the angle between the voltage and the current. So you will get an phi u minus phi I, and then this will be the expression for the apparent power, total power in the circuit. Now, another aspect is the flow of power. Here we can see that it's not really like a pure reactive or pure resistant circuit, but then the theta, the angle between, or the phi I had earlier, will then decide like how long apart the voltage and the current are. When we have like a P plus, the positive current, that means current flowing in the direction of the voltage drop. So in the direction. So the rate of transfer energy are to the load. And also remember that this angle is positive for current lagging. So by definition we know that the power absorbed inside this box, if you look at this figure, is this, as I have already expressed. Now what we see here is an idle voltage source. That means it's a constant magnitude, constant frequency, and zero impedance. And often working in simplified evaluation and calculation, we use an idle voltage source. And if you want to measure power in such a system, you need a wattmeter with a current coil and a voltage coil. And of course, it's a product between them. So for an AC system, as you can see here, shows within the box an idle voltage with polarity marked to indicate, as usual, the terminal which is positive during the half cycle of the positive instant voltage. Similarly, the arrow indicates the direction of current I into the box during its current positive half cycle. And the voltmeter, as I said, has a current coil, voltage coil. So to measure then the active power. And the coils must be correctly connected, so as to obtain upscale reading. Let's look at our case here. We have two voltage source or absorbing. Is two idle voltage sources is designated as machines 1 and 2 are connected, as shown in figure. If the impedance between machine 1 and 2 is in this minus J imaginary value of 5 ohm, and the voltage E1 and E2 is like this, we can then have an expression for the current, and looking like this. So the current leaving box 1 is plus 1 from 1 to 2. To see if the machine is generating absorbing, we have one voltage source, E1 here, calculating. E1 times the current complex conjugated. It come like this, and then we have the E2 times the current complex conjugated here. And this will be the expression. So machine is a generator which produces active power and draws reactive power from the grid. As you can see, machine generates 1000 watt, receives 268 var. Machine 2 absorbs 1000 watt and receives 268 var. And it's a purely reactive supplies, so there's no P is consumed by the impedance. And it could, of course, machine may that it be expected to be a generator because of the current direction polarity, but you always have to check with when you're calculating the power. To sum up, this is to give an overview of direction of power flow. So if active power is larger than 0, the circuit absorbs real power. P is less than 0, circuit supplies real power. So if Q is larger than 0, circuit absorbs reactive power, so E as the current lags voltage. And if Q is less than 0, the circuit supplies reactive power. The current then leads the voltage.